Okay, we're continuing on now. We're going to stay with right triangles, but what we want to do is look at a few critical geometric calculations related to the right triangle that are going to then play into our unit circle discussion. So, I brought an umbrella and a stick today, and I want you folks to use your pencil in standard angle orientation. So here's an example, and I want you to hold your pencil in the air just to see if you know your angles. Okay? Hold your pencil at a standard angle of 60 degrees. A lot of you, it looks like, are down here around 45 degrees. Should be steeper. 60 degrees, right? Not straight up, like in the back there. 60. Hey. Oh, there we go. Okay, good. Okay. Okay, 30 degrees. 30 degrees. Okay. Now let's say my umbrella is of length 1. Length 1. How high is the tip of the umbrella right now at 0 degrees? 0. Okay. How high is it when I'm at 90 degrees? It's up at 1, isn't it? I'll hold it lower so it shows up in the image. Okay. It's up at 1, isn't it? Now notice what happens as I move the tip of the umbrella in circular motion. It's rising from a height of 0 up as high as 1. Right? Now think about what's going on here related to what we just talked about in the previous segment. We talked about, if this is my angle inside here, we're talking about this opposite side over here divided by 1. That's what ratio? Opposite divided by hypotenuse. Sine. So the sine of this angle between the two sticks, the sine of the angle is growing from 0 in value to as big a value as it can get, a value of 1. Right? If I go past those acute angles, if I go past 90 degrees, what's happening to that height? It's coming back down, isn't it? Okay, this is a mental image that you can have. So let me have you hold your pens at 120 degrees. 120 degrees. Not 150, but 120. Thank you. Okay. It's up here. It's up here. It's not down here. Okay? So that height there, if this is 1 now, if that height is clearly less than 1. And as you continue towards 180 degrees, it's coming down towards 0. Now what if I go back past 180? So here's my sticks. See my big angle now, bigger than 180 there? What's happening to that Y reading of the tip of the umbrella? It's negative. And how low can it go? -1, right? Can't go any lower than -1. And then if I keep rotating, except my arm's getting twisted, okay? If I go past 270, then what's the tip of the umbrella doing? It's coming up from -1 towards 0. And then if I go past 360, what's it doing? It's rising again, isn't it? Towards 1. So do you see the fact that those values start repeating themselves? They start repeating themselves if I go all the way around there? Okay? That's our first trig function. It varies. It changes value. From 0 up to 1, back to 0, goes down as low as -1, comes back to 0, and then it just keeps on doing that, cycling up and down. Okay. There are lots of things in the world, in life, that do that. You hook a spring with a little weight on the bottom of it, and you pull it down and let it go. What's it do? Boing, 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 bounces back and forth, doesn't it? Okay. And we're going to study that real soon. Okay. That motion, that oscillating motion, is called a sinusoid. Fancy word. Just something that's cycling like I was just describing. Okay, so let's come back and do a couple simple geometric problems here. Important ones. Let's see. If I took a 45-degree right triangle, that's not too good. Let's make a little more accurate here. .45 degrees. And let me force this hypotenuse to be 1. Force the hypotenuse to be 1. Now, what do you know about this triangle I just drew, besides the fact that there's a right angle right there? The side lengths are the same, right? This leg and that leg are both the same. So why don't I call them both A, because we know that they are the same length. Right? Okay. Oh, let's look at this. Let's look at the tangent of angle theta. Let's look at the tangent here of, let's let that angle be 45 degrees. By definition of tangent, it's opposite over adjacent, right? Opposite over adjacent. Oh, the tangent of 45 degrees is 1. Yes, Alyssa?
Are the sides also the square root of the hypotenuse?
Oh, yeah, they will be. We're going to do that in just a second. Yeah, we're going to figure out the actual links here. Okay? We're going to figure out those links in just a second. Is that all right with everyone? Okay. Now, let's go back to beginning algebra with my umbrella. Beginning algebra. If I have a line, a straight line, where my umbrella is at 45 degrees, what's its slope? 1, right? We all know that. The rise is the same as the run. Okay, so the slope is 1. Well, that's kind of interesting. This tangent of 45 degrees is the slope of that terminal side right there. Yes?
Is that always the case, or is it just a coincidence here?
Well,
I guess
it's a coincidence here. And what we want to do is see what happens when we start talking about tangents of other angles. Seem reasonable? Okay. So we're becoming a little inquisitive about this. Okay, there's some connections that it might be happening. Now let's do our Pythagorean theorem game on this. Leg squared plus leg squared equals hypotenuse squared. We all know how to do that. A squared plus A squared equals 1 squared. Well, let's see. Let's do some algebra. Twice A squared equals 1. Isolate it. A squared equals 1/2. Pythagorean theorem, right? Let's crank it out. Square root both sides. A equals plus or minus the square root of 1/2, which we know is the same as plus or minus 1 over the square root of 2. Right? Do we leave it that way? No. What we do is we rationalize the denominator like we did previously. So we're now going to multiply top and bottom there by square root of 2. Numerator and denominator, and we end up with plus or minus square root of 2 over 2. If we lock this into our xy coordinate system, and we have an angle at 45 degrees, and we have a terminal side of length 1, then this height right here is going to be square root of 2 over 2, and this leg right here is going to be square root of 2 over 2. Everything okay? Takes you back to beginning algebra, doing the math here, and we find that each of these legs are exactly the same value, and they happen to be square root of 2 over 2. Now there's an important value, actual number there that I'd like you to kind of have in your head, because you're going to be punching things like tangent of 45 degrees with your calculator. You'll be doing things like the sine or cosine of 45 degrees, okay? And you want to have a sense of what the value is. So if we actually did the arithmetic or did the math here with a calculator, this is approximately plus or minus 0.707. There was an old jet airplane, one of the first major commercial jets that came out, the Boeing 707. Really noisy thing when I was a kid. Very noisy. But it was a very popular jet. So that'll help you memorize that if you want to go back and look at some of those old planes. Okay. Feel good? Now, look at this. What's the sine of 45 degrees? By definition here.
2 over 2. Square root 2 over 2 over 1.
Sine of 45 degrees is your opposite, radical 2 over 2 divided by 1. Right? So it's just radical 2 over 2. How about the cosine of 45 degrees? Same thing, right? Adjacent side over hypotenuse, radical 2 over 2. So we have 3 trig ratios here for 45 degrees that we already know. Pretty handy. If you don't think it's handy, you will after you've done some homework. Okay. All right. What if I scaled this triangle larger or smaller? What if I scaled it up, made it bigger? Yeah. Yeah. Won't those ratios still reduce back? Because isn't this little triangle here similar to that big giant one? And the ratios of the sides will still be the same? Okay. So you're going to love having a hypotenuse of 1. Okay? You see how this relates to something I'm going to talk about in a little bit called the unit circle? A circle of radius 1. Okay. So that it's going to all tie together here in a couple minutes. Okay. What other comment? Oh. Was anybody puzzled by the plus or minus and the fact that I didn't say anything about the minus? I mean, we know it's plus or minus when you extract the root of a quadratic expression like this, right? You get plus or minus possibilities. Well, watch what happens, folks, if we went to negative 45 degrees. Wouldn't that be sitting right down here? Like that? With the hypotenuse still a 1? What's this length right here? Yeah, isn't it negative if we're thinking of x and y values? Isn't it a negative value? Negative square root of 2 over 2. So what do you think the sine of negative 45 degrees is? Opposite over hypotenuse, again, negative 40 radical 2 over 2. So the sine of negative 45 degrees is the same as, oh, watch this. I'm going to be spinning my umbrella in the air pretty soon with you, okay? Because we're going to be at different, remember those 16 angles we talked about a few sessions ago? We're going to be taking our umbrella and putting it at different angle locations and being able mentally to tell what the angle, what the trig ratios are, just by knowing the direction the angle sits, the terminal side. So if I'm at the sine of negative 45 degrees, I look in here. Here's my measure of the angle, right? And I look at the opposite side, hypotenuse, and I have negative radical 2 over 2. So excited about using the umbrella. Let's do it. Watch this. 315 degrees. all the way around to right there. Right? All the way around to that same direction. So what would be the answer to the sine? Well, actually, this is going to get a little weird because you're going to go, oh, that's not a triangle anymore. Yeah, it's going to be a little disturbing to you at this point. But just bear with me. Okay. Do you kind of see that that opposite, so that y value there is the same as it was with the negative 45? Okay. So I'm going to have to kind of lead you into that, right? So the sine of 315 degrees is going to be the same as the sine of minus 45 degrees. And I have to kind of redefine our ratios because the fact that I'm not dealing really with this triangle anymore once I go past the acute angle shown in here.
If it's plus or minus for positive 45, isn't it plus or minus for negative 45?
Sure, when you do the math. But what I commented on here is if you think of this in terms of the x and y axis system, then if you're down here, that's going to be clearly a negative reading. Okay, so that's all. So think of it in terms of laying this onto an xy axis system. Let's do another geometric calculation, important one. So much of this stuff just builds on those things back from beginning algebra level and with a lot of new vocabulary thrown in. Let's draw a new triangle, and I'm going to lay it on our xy axis system. This time I'm going to let the angle be 30 degrees. And I'm going to stick with a hypotenuse of 1, and this time I'm at 30 degrees. Now, we do not have anything nice here about the relationship between those two sides other than knowing that the y value is less than the x value, right? You can see it. That's shorter than this, right? And isn't the slope of that less than 1? Slope is less than 1, clearly. Okay. All right. So here's a little simple trick. If I take and draw a negative 30 degree angle, also on here, with this hypotenuse length of 1, right? I got plus 30 degrees. I also draw a negative 30 degrees. And so by these two sides being the same length, then this triangle is isosceles. Isosceles. This angle, this vertex angle in that big triangle now is 60 degrees. If this triangle is isosceles, then that means these two angles have to be identical, which means each of those have to split the 120 degrees remaining. So each of them have to be 60 degrees, don't they? Matter of fact, we knew that was 60 degrees in the original triangle because we had a 30, 90, and that had to be 60. So this is what kind of a triangle here? Oh, the big one? Equilateral. Some of that vocabulary is why you're supposed to have had geometry before you took this course. Know that some of the vocabulary, okay? So this is all three sides are equal, and you see the symmetry? So therefore the height right here has to be clearly a half. And that one has to be negative 1/2 if you think of it in terms of the y reading. Simple. We like that. What's the sine of 30 degrees? Opposite over hypotenuse. Again, it's the y reading you see right there. It's the y value you see right there, 1/2. What is the sine of minus 30 degrees? You have this triangle down below here, the y reading there, negative 1/2. Opposite over hypotenuse. What's missing on that triangle? the length of the adjacent side. Right? Length of the adjacent side, we haven't done that yet. So it's going to be the square root of the hypotenuse squared minus the other leg squared. Right? So this has to be the square root of the hypotenuse squared minus that other leg squared, which is the square root of 1 take away 1/4, which is the square root of 3/4. The square root of a ratio is equal to the ratio of the square roots. So we end up with that side being the square root of 3 divided by square root of 4, which is 2. Two very important values here, 1/2, and this one down here, square root of 3/2. Any difficulty with this? Can you keep the three numbers we've come up with in your brain? Everybody can do that, right? 1/2, square root of 2/2, and square root of 3/2. Easy. So looking up here at this picture, what's the cosine of 30 degrees? It's the cosine of this original 30 degrees. Adjacent over hypotenuse. Yeah, so the cosine of 30 degrees is equal to square root of 3/2. The cosine of negative 30 degrees here's the picture right here, the lower triangle right here. The cosine of that is the adjacent side, square root of 3/2 divided by 1. Again, square root of 3/2. How you feeling?
Why is it not the negative square root of 3/2?
Excuse me?
Why is it not the negative square root of 3/2?
Because that line is
Well,
on the x-axis, that makes
it-
square root of 3/2 is
Good comment. Yeah, you said the line here is a positive reading, isn't it? Isn't that a positive x reading?
Yeah.
Yeah, that's why. That's why. Alyssa?
So it doesn't matter if the one is negative slope or anything?
Down here? No, not for sine or cosine. But it does for tangent. I didn't mention tangent yet on this one, did I? We did tangent here with a 45, but we didn't do the tangent of this guy. So the tangent of 30 degrees, let me put it up here, is going to be, I'm going to have my triangle in my head. I have that mental image. This is important geometry now, right? And I have the mental image of this triangle in my head with those three numbers, 1/2, square root of 3/2 here, and the 1. And so the tangent is opposite of the 30 degrees is 1/2 divided by this side, square root of 3/2. I'm going to erase some of this on the board here.
On the bottom half of the triangle, you should have
Yeah, but let's stick with the upper one first. Tangent of 30 degrees, I'm going to have that image in my head, and I'm going to have my opposite side as 1/2. My adjacent side is square root of 3/2. So I have a complex fraction. If I multiply numerator and denominator by 2, I'm just multiplying by 1, right? I lose the 2's, and I get 1 over square root of 3. But we don't leave it that way, do we? We multiply top and bottom by radical 3, and so we get square root of 3/3 for the tangent of 30 degrees. So we have the sine and cosine of 30 degrees. And here's our tangent of 30 degrees in exact form. Observe, if you punch this on a calculator, that this value is smaller than 1. Less than 1. Happens to be the slope of this terminal side. Like where I used the umbrella earlier. The slope of that is clearly less than 1. If you punch this value on a calculator, you'll get a value less than 1. Which you should. Opposite over adjacent. All right. What about 60 degrees? Do we have to do a whole new geometry problem? What about 60 degrees? We've got the three sides of a right triangle involving 30 degrees. Well, there's 60 degrees sitting right there. So what if I take and put this in my standard angle form, same triangle with a hypotenuse of 1. This time I turn it and I make this angle 60 degrees. This leg right here is clearly 1/2, and that other leg is clearly square root of 3 over 2. So we don't have to do a new problem. All we do is take that triangle and turn it. So what's the sine of 60 degrees? Square root of 3 over 2. The cosine is the adjacent side over the hypotenuse, 1/2. And the tangent of 60 degrees, opposite over adjacent. And what reduces out? This divided by this. This divided by this. The 2 reduces out, and you're left with square root of 3. Notice this value right here is greater than 1. Greater than 1 right here. Clearly, the slope of this is greater than 1. Again, think beginning algebra. Rise over run. Tangent, you can think of tangent as the slope of the terminal side. Everybody still awake? I've been talking all this time. I should have you folks doing something, but I'm trying to get through all this so that you've got enough to go with for homework and stuff. Yeah. Stormy?
Split the triangle for convenience, correct?
Yeah.
Okay.
No changes in the numbers, is there? Yeah.
But we can leave it this way. I mean, it's
Sure. Well, if your standard angle's 30 degrees or minus 30,
right.
you can do it, lay it this way. But what if you're at 60 degrees? Or what radian measure would this be? This angle. What radian measure? Okay. Here's pi. Here's pi, right? There's pi. It's 1/3 of pi, isn't it? You folks better go eat some cake or something and cut that thing into different size slices, okay? All right. Okay. Get good at that. Okay, those are the geometric calculations I wanted to go through with you. I want you to have those 3 numbers in your head. And then now what I want to do is end this segment, and then we'll go on to the next segment, which will be the introduction to the unit circle. And after the music stops, I'll take a couple questions while they're queuing things up.